Hello and welcome to a new rubber duck programming video. I am George and today we will write a function that determines whether an integer is prime. I will be writing the code and at the same time explain the reason behind my thought process. So let us begin. I will create a new project in Java using the NetBeans IDE and I will name it primes. After creating this project, I will start coding. Let's see here. Yes, let's delete this and get to it. First thing I'm gonna do is create a public static boolean is prime, and it's gonna take as input an integer and return whether or not it is a prime. So what is a prime number? A prime number is an integer, a natural number, which is 1, 2, 3, 4, 5, 6, no fractions, no irrational numbers, no decimals, no negative numbers, just the natural ones, 1, 2, 3, etc., that is only divisible by itself and 1. So by this definition, 2 is a prime number because it can be divided by 2 and 1. 3 is prime because it's divisible by 3. It's not divisible by 2 because it's 1.5. It's not an integer division. And it's divisible by 1. Every number is divisible by 1. Anyway, so let's get to it. 4 is not a prime number because it's divisible by itself, by 2. 4 divided by 2 is 2, and it's of course divisible by 1. Following this reasoning, 5 is prime, 6 is not prime because it's divisible by 3 and 2, and, other than of course 6 and 1. So let's get to it. How do we determine whether or not a number is prime? What we do of course is check all the numbers smaller than all the smaller numbers, whether or not they divide them. So what I'm gonna do is create a for loop that starts from somewhere. It's not gonna be 0 and it's gonna be less than the number itself. So I++, and I'm gonna check whether or not it divides completely. How I'm gonna do that? I will not do the division. Sorry, I will not do the division, I will do the modulo of the division, which is the remainder. So therefore, if the modulo is 0, I divides n perfectly, and which means that the number we are looking for is not prime, so we return false. If we search all the numbers and find none of these divides n perfectly, we will return true. Now, what is the range at which we want to search? Of course, we can't search from 0 because we won't divide by 0. That's not correct, and we are not going to return false if n is divisible by n. It's of course quite it's obvious that it does. So should I begin with 1? But every number is divisible by 1, and 1 should not return false because according to the definition of the prime numbers, primes are indeed divisible by 1 and of course themselves. So I will begin with 2. I will start with 2, and actually oh yes, it's less than n, so it's not less than equal to n, so it's not gonna try to divide n by n. But actually this is not really necessary to look all the way up to n, because if we are going to look at large numbers, we only need to check the dividers of the square root. Math of the square root of n. Why? Because and equal to the square root of n. So, for example, if we're looking to determine whether the number 25 or the number 9 is prime, it's gonna search up to 3, the square root of 9. There's no point looking into the square root of any larger number than the square root of n, or 9 in our case, because let's say we're looking after 3, 4. If 9 was divisible by 4, then it would be also divisible by 2, or some other such number, a smaller one than the actual factor. So this is straightforward as that. Let's go into the main function and try to present our results. So from 0, no, we won't begin from 0. I will try to print out all the prime numbers from 2 to 20, and including 20. So here I'm gonna do system out printf and the number here, the integer, and whether or not it is prime. So let's say I will print this I. Let's put some brackets in here, and then I'm gonna have an if statement is prime. If I is prime, then I will also print out that is prime \n, and if not, I will print out that it is not a prime. So let's see, have I written this code right? I will run this. Let's run it and see what happens. So let's begin. 2 is prime, 3 is prime, 4 is not a prime, 5, 6, 7, 7 is prime, 8, 9 is not a prime, yes, 10, 11 is indeed prime, and 13. So 14, 15, 16 are not, 17 is, 19 is, let's see, up to 25. I will like this to see whether this works okay. And so 25 is not a prime because it's divisible by 5. And it had to look up to and including the square root of n to determine whether it is a prime or not. So there you have it, a simple, concise function that determines whether an integer is prime. Next up, we will write the sieve of Eratosthenes. It is a function that finds all the prime numbers less than or equal to a given number. Thanks for keeping up with me, and I'll see you next time.